Okay, so over the last couple of days, we've been talking about EMR. Let's do a quick bit of review because it's been a weekend. Maybe you've forgotten some stuff. What is EMR? What does it stand for? Well, first of all, the acronym EMR, electromagnetic radiation. I think most people are pretty good at understanding, well, okay, radiation, I've heard of that before, okay? But I need you guys to know the cause of radiation. What causes radiation? Accelerated charged particles. Okay? Whenever a charged particle accelerates or even decelerates, by the way, that counts too, it emits EMR. Does anybody know how an X-ray works? How does an X-ray work? Oh, okay. I should be more specific. Does anybody know how to create X-rays? There we go. Anybody know how to create X-rays? Maybe you know how the X-ray works in terms of it's showing a picture of your bone, but do you know what the machine does to make an X-ray? Yeah. And then it rams them into a piece of lead. Okay. I think it's lead. It's some sort of sheet of metal. Okay. And when those electrons run into this highly dense sheet of metal, they rapidly decelerate. Okay. Now we've learned that anytime a charged particle undergoes an acceleration or a deceleration, that will emit a magnetic wave. You guys remember your first-hand rule? If you have a charged particle going in a certain direction, a wave will go in a perpendicular direction around it. But what happens when you start making a magnetic wave? Magnetic waves make electric waves. And electric waves then make magnetic, and so on and so on. And the classic picture, I can't draw the best, but hopefully you've seen this picture before, is that a wave is traveling this direction, and you have a magnetic wave going up and down, say taking the y-axis. And so this could be a magnetic field happening here. Coming out of the page in a perpendicular direction to it is an electric field. And the magnetic makes an electric, which makes a magnetic, which makes an electric. And so then you end up with a picture that looks something like this. Do you guys recall this from a previous day's notes? So James Maxwell, yeah, it's on the front of the progress log even, thank you. James Maxwell then came up with some hypotheses and some equations. We don't actually use the Maxwell equations, but he predicted how EMR would work. Okay, and Heinrich Hertz made an experiment where he basically sent the first radio wave. Right? And basically the idea was, if I can kind of illustrate this, is he sent a current running between this and this, and he ran this to a battery. So imagine this is a battery, positive, negative poles, and the electrons are running through this, and the battery causes a spark to oscillate across this little beam right here. Well, he set up a receiver over here, same distance apart, and this receiver also had a spark show up. And literally what was happening is a wave was being transmitted. And that was really the first radio wave ever being used. Do you guys remember that short little YouTube video I kind of showed with that? I can play it again if you want one day. Okay. So that was Heinrich Hertz. Now, really all of this then is basing on the concept of, well, what is EMR? And so hopefully you guys are familiar with the idea that electromagnetic radiation is really a spectrum that keeps getting higher and higher frequencies. Somewhere in the middle, we have visible light. And then on opposite ends, we have things like radio waves. We have X-rays. Nope, that's not right. We have microwaves. We even have infrared. And then on this side, you have your UV rays, your X-rays, and your, what's next, gamma rays. What's similar between all of these things on this end of the spectrum? They're all dangerous. Many of them are cancer-causing. Whereas these things right here, they have such a long wavelength that they're really not dangerous. These guys right here have a very short wavelength and very high frequencies that they can penetrate into skin and bone like X-rays can. So anyways, this is something else you guys should know. Another thing I wanted to talk about a bit was the idea of light being either a particle or is it a wave? And if we're making a pro-con list for evidence for both of them, yeah. Radio waves go around us. They're so big that they'll actually go around things. Yeah. So, yeah. Anyways, good question. Evidence for light being a particle would be something like this, reflection. And we spent some time talking about how if you have a mirror and a wave comes bouncing in, it kind of makes sense that it just bounces right back out at the exact same angles of incidence and reflection. Okay. And we even talked about some properties of some curved mirrors, like this concave mirror, similar sort of stuff there. And that would be evidence that light's a particle because it bounces off of things. However, there was also evidence that light was a wave. And one example of light being a wave is that if light comes into a medium, it could actually bend through that medium. And sometimes it actually bends like to a closer angle than it was before. This would now be a thicker medium because it's actually bending inwards. And that really seems to indicate that light's more of a wave because particles don't really bend. Today we're going to build on this concept of, is light a wave or a particle? And we're going to talk about two things, diffraction first, and then interference, and how this has given rise to more evidence that light is probably a wave. But it's actually also a particle. Okay. Our last topic is going to be something called wave-particle duality, and how EMR actually behaves as both in this really weird quantum state. I think it's cool, actually. So, for the longest time, you guys maybe even remember me telling this anecdote. Isaac Newton believed that light was a particle, and nobody disagreed with him, because he was like the great Sir Isaac Newton. And so if he said it, it must be true. And so, in a way, he almost like stilted scientific progress on this, because no one wanted to try to argue with him. So, anyways, let's start our new set of notes now. Yeah, it's both. That's what we're going to discuss more, is that it behaves as a particle sometimes, and as a wave other times. And that's what makes physics so weird and cool. So, anyways, let's talk about some evidence here of Newton's model. Newton thought it was a light, it was a particle. Okay, and eventually people started thinking, well, maybe it's more of a wave. Okay, one of them is this principle here. It's Huygens' principle of diffraction, and we've already kind of witnessed this in certain cases here. If we were to like send a wave through like an opening, we actually can see it re-spreading out again, right? And like this picture here kind of illustrates the idea. Let's say that a wave was sent through here. Okay. All of these lines here represent a wave front, if that makes sense. If you know what a wave front is, it's like the peak. This is the top amplitude, for example. Okay. And it can actually go around corners. Okay. Now, let me give an example of this. Imagine I turned all the lights off. Would it be perfectly dark in this classroom? Well, no, because is there light still getting in from outside? Yeah, but is the light coming in through that window? Does it have to go in a straight line? Or after it comes into that window, does it kind of like bend around the corner a little bit? And like it does, like the light will still fill the room. It will diffract around the edges. Does that make sense? I mean, we still get shadows sometimes, right? A shadow is where it's really blocked. So like there's a shadow right here, right? This is a shadow area where light couldn't get through. But it does have the ability to go around corners. And you guys have probably seen this, maybe not with light waves, but I've got a great picture here of water waves. I found this picture online. I think it illustrates my point. Imagine that some water is coming through this like port, this opening right here, right? And as it's coming through, does the water literally just keep going in a straight line, a linear path for forever? Well, no, it spreads out. And it starts to make these wave fronts where it's kind of curved like this. You get what I'm saying here? That's called diffraction. And light also does this, right? For example, like let's just take underneath your chair, okay? Light is up top here, and underneath your chair, I can see some shadows because some of the light is being blocked by things, right? But is it completely black where there's like, I can't literally see a thing? Well, no. Sometimes it's a little bit fuzzy even, depending on like how the light has bent around corners. That's this picture right here. Light has the ability to basically, in a wavefront, start bending around things, right? Over here, sure, this is where a shadow region is. So that's called diffraction. Okay. I got a lot more pictures to kind of illustrate the same thing, but I imagine that you guys kind of get this concept, okay? If light was purely a particle, as light particles came out of a barrier, this would be a shadow right here. But we don't see this. We see light behave as a wave and kind of go around the corners a bit. Yeah. That's true. But I think we'd argue there is that when people go outside the door, they have their own energy to go off into different directions here. If I were to like shoot something on a trajectory out the door, though, it wouldn't bend to the sides, though, would it? Well, this is what we actually, you know the answer to where I'm going with this, though, right? Because we're going to eventually talk about the double slit experiment. But like, does that make sense, though, that if this was on a trajectory that was never going to be changed, yes, it would do that. Do people have the ability to go this way here? I guess, but that's because they add more energy and they just choose to walk that way. So, anyways, yeah, this is what we've discovered, though, is that these shadows, the light can actually go around the corner. Maybe here's some more pictures to make sure you understand what I'm referring to here. Whenever you see these kind of like circular pictures right here, what that's meaning is that, remember, a wave is going up and down and up and down and up and down and up like this, right? It's got this period and amplitude idea to it. Whenever you see like a circle like this and like this and like this, it's probably referring to like the peak. And so this is the highest point of a wave, and this is the highest point of a wave, and this is the highest point of the wave. So what does that mean for like halfway in between? What's happening halfway in between here? That would then be the lowest point of the wave. Right? So this is high, low, high, low, high, low, high, as really the wave is going up and down and up and down and up and down. But because it's really hard to measure it in 3 dimensions, we sometimes draw these things here. They're called a wave front. Do you guys see those in Physics 20 at all from whoever taught you in Physics 20, the idea of a wave front? Okay, maybe not. So that's what this image really is showing here, is that all of these are a wave front. And if you could almost picture it sideways, this is when the wave is at its highest, then lowest, then highest, then lowest, high, low, high, low. And what we're representing is just the peaks of all of them. Okay, I actually skipped something on one of my first slides. I actually want to go back to that. I realized I didn't talk about it here. Up here, remember how I talked about Newton really believed in the particle model? And like no one was able to challenge him on this? There were 3 main concepts which help prove that light can also, not or, but also be a wave. It can actually do both. Okay? So the first one was this Huygens principle of diffraction. Light goes around corners. This next one is very influential. This experiment here you guys need to know about. It's called Young's double slit experiment, and we're going to replicate it on Thursday. I'm even going to show you it today a little bit. Here's what Young did. He assumed that if he had like this big piece of, I don't know, metal in the way, and he had 2 little, like he called them slits, 2 little holes in it, he assumed that if light was a particle, here's what would happen. Light would go here, and it would bounce and go, okay, can't go through. And it would go here, it would bounce here, couldn't go through. But maybe light could go through here, it would phase right through the hole, and what he assumed is you would see 2 lines on the other side. He figured if light was a particle, this is what should happen. Made logical sense, right? It would just keep going in a straight trajectory. However, we now know that light behaves in these wave fronts, and so it's actually going to spread out. Here's what actually occurred. As he sent the light through these slits right here, 2 consecutive wave fronts occurred. So can you see how you got like one set of circles kind of coming out of this? Where's my drawing tool here? One set of circles coming through here. Come on. Apparently I can't draw anymore. Weird. Give me a second. I'm just going to reset my board. Here, give me a second here, guys. I'm going to turn my board on and off. Let's try this again. I can't draw. That is so weird. I can go to the desktop. I can draw there. I think I'm going to have to split this video into 2 sections here. I can't draw anymore, so I'm just going to stop the recording, start over again.